So, welcome back from the break. Please welcome Vladimir and Fredrik for the last talk for today. They are talking about IoT architecture and processes. So, please, the stage is yours.
Awesome. Yeah, thanks very much for having us here. Just a little bit of background on who we are and what we do. We basically work together in telecom security and consulting, and we work across a number of critical infrastructure domains, do a bit of training, but we're really interested in doing research into security appliances, including telecom appliances as well. And this is kind of where this talk comes from. Is surprisingly, there's a lot of IoT in telecom. You wouldn't expect it to be there, but most of the devices that run really critical systems are running on ARM and Spark and PowerPC and things like this. And those devices are hard to come by, so we are basically given this talk to think about how to virtualize systems and IoT systems and find issues and elements and issues and vulnerabilities in them. Some of the previous talks we did briefly basically build upon that. So last year I did a talk around sandbox security, critical infrastructure security, and basically attacking security applications and firmware as well. So this talk is basically going to discuss kind of why IoT applications, why they're in critical infrastructure and how they work. We'll talk about the IoT hardware, OS, and application layers. We'll look at case studies of a number of IoT systems that work in critical infrastructure and kind of by themselves. And we'll look at some of the ways we, found issues in them. I'll look at extracting firmware within the systems, and then really mainly we built a tool that we nicknamed the Malware Factory to help virtualize all the IoT processes out there, 14 of them, and how to automate the creation of IoT testbeds and environments to actually help build and find problems. So kind of why talk about IoT? Well, most vulnerabilities where people discuss things are things like default credentials that we hear quite frequently. DOS attacks, due to low CPU cycles and low processors, poor physical controls, and kind of the insecure web interfaces that we see quite frequently. We wanted to look at a slightly different approach, and we're looking at kind of the binaries and then the actual processes across IoT devices, what they are and what issues they can pose if you know how to reverse them. When I say IoT critical infrastructure, we're kind of talking about telecom specifically, but also within things like power plants, within cars, within factories, anywhere like that. So for example, VxWorks is an access system used within telecom environments to be able to monitor and look at things like MMEs, HSSs. That runs mainly of PowerPC and ARM. The MSsoft X3000 is a Huawei-based, all-encompassing system for open core. Again, mainly runs on IoT processors. And the ASR 5000 is a GGSN, SGSN, packet gateway, again, used within telecom networks. Also kind of runs the Broadcom chips, the ARM chips, and some x86 as well. So kind of understanding these processors becomes quite relevant in having to defend these systems. There are also specific devices as well. So some of these devices include things like GSM gateways, SIM banks, radio over IP, for example, all IoT, solar panels, and even full mobile cores. So there's a project called OpenEPC, which is Open Evolved Packet Core, and it's a 4G core that's built completely on IoT architecture. It has deployments within things like police cars, where within actually the car itself, they'll be running its own custom mobile core, so then other systems can connect to it, phones can attach to it, can do the full authentication process, and that's built all on top of IoT systems. So to be able to test and understand these systems, we wanted to look at actually creating an environment and create a kind of a virtualized structure to be able to then go through and look at every processor that was available and find ways to instrument, fuzz, mount, and attack the systems. So basically, the idea was to create something that was automated, would allow us to do binary instrumentation and fuzzing, could do full device virtualization. We wanted to run firmware just from binary, just from firmware updates. So we didn't have, I guess, the funds to buy every single IoT device available, but a lot of firmware updates give you enough information to be able to actually download and run and set up the system yourself. Also, learning new processors that have never been used before is kind of interesting to create new machines, and understanding the environments of these IoT systems. So I'll let you
sure.
take over.
So if we take a look at the anatomy of an IoT device, it consists of essentially three parts. It has a hardware part, because it needs to have something to run on. It needs to have an operating system that runs on it, that you can run your applications on. And of course, it has the applications as well. So the first thing you need is a processor, and there are quite a few to choose from, but the main three ones is ARM, which is the massive market leader. It's pretty much everything that's built right nowadays is ARM or MIPS or PowerPC, but ARM is definitely the absolutely biggest share. MIPS is in second place and fairly common, but still nowhere near the ARM. PowerPC is rare, but definitely present. You can find it in some smart TVs and things like this. There are exotic processors floating around as well, like Blackfin, but that's more for, well, rare cases and maybe targeting systems for military things.
The actually interesting thing is we found a Blackfin processor within a GSM kind of 3G gateway, and it was actually quite a challenge because the older firmware of this gateway we couldn't put into IDA, we couldn't reverse it properly because IDA doesn't understand Blackfin instructions. Yeah. Luckily, with the update for that GSM gateway, they went to ARM, which was really nice for us. So then we got the new firmware and managed to step through that without a problem. Yeah. But that actually, I think, poses an interesting defensive idea. We use processors that many other people don't understand.
Yeah, because not many people will go through the trouble of making an IDA module, processor module for just one target. Right?
In fact, Fred suggested building one. I said, no, let's just focus on another system. I think you have to pick your battles here.
Well. So in addition to a processor, you need some kind of storage. And very often it's an SD card embedded into the solution. You see that also in Chinese, cheap Chinese phones often have an SD card rather than actually some NAND flash. But NAND flash or an SD card to store your operating system on and run stuff from. And you need I/O capability. And I've included a picture of a development board here. It's a Raspberry Pi. But there are many types of development boards specifically for IoT. And they generally come with some general purpose in-out pins so that you can put your sensors or diodes or whatever you have to measure your environment or whatever you want to do. They might also have USB ports, Ethernet ports, HDMI for visuals or just video out in terms of things like Orange Pi, etc. And they also have connectivity in some ways on the radio side. For example, GSM, LTE, or some IoT devices have very narrow band radio interfaces that are not standard mobile interfaces. They're more like, well, very narrow band, very low power, and these low power devices are thrown somewhere in the jungle and just sits there on battery for 5 years. When it comes to the operating system, there is often you find a cookie cutter type Linux installation in the bottom of these things. And those are built using some very popular frameworks. One is called BuildRoute, for example, and we also have Yocto Open Embedded. These frameworks allows you to build a very streamlined and small installation of Linux with mainly tried and tested components. So it's a very practical way, but it also detaches the developer a little bit from the actual process of building something. And that also spills over to security thinking, of course. Sometimes we see proprietary OSs or exotic OSs in these boxes, but that's something completely different from this talk. So if you take a look at BuildRoute as an example, this is one of the most popular frameworks. It allows you to select a multitude of options. You have the tool chain, for example, is a very important part, which lets you select which C libraries to use, etc. And you also get to choose kernel version, of course, target packages. And the first thing you choose is, of course, which chip you're building it for. In this case, Little Endian ARM, which is essentially the only ARM processor you'll be seeing in deployments today because no one uses Big Endian. But you get to select between a lot of different options here. And then you get to choose which C runtime you want to build for. And you have, for example, uclibc, which is very often seen in IoT. glibc is a bit more rare, but it's there. And you have Muzzle as well, which is supposed to be a little bit more secure and more lightweight. And with this C library, you also get a tool chain. And this tool chain is, of course, built on the host machine that you're compiling on. So you're building the whole, let's say, the whole deployment on a x86 or x64 machine, and you can also then build binaries on that machine for this specific deployment, even if it's for another chip. So that's a cross-compiler toolchain. Yes, target packages. These frameworks also come with a very large set of applications that you can use. So there are different audio and video applications, for example, file system utilities. You can have SSHFS, for example. You can have different networking applications. interpreters, and even mail applications and web servers and things like this. So you get to choose here from a wide selection of components. So much of this is so very automated that it becomes, well, essentially point and click to build your own firmware. And BuildRoute, for example, comes with a lot of pre-configured development boards. So you can just select the board that you bought to develop for, and you have a baseline configuration, and then you add your applications or whatever you want. So the result is generally a limited size the Linux deployment, very highly customized. So it's supposed to be limited in size, which it is very easy, you just don't select anything. Limited in functionality, so you don't expose more than you actually need to. And hopefully also limited in vulnerability. But that's not always the case. And then I think we get into applications, which is where we add the vulnerabilities, generally.
Yeah, so of course, a lot of these systems run a mishmash of applications, third-party libraries. A lot of stuff is out of date. They have a lot of the things, a lot of times, customized security functions, and we'll cover what some of those are. Custom parsers is, of course, another big issue that we come across quite frequently within IoT devices because of like custom APIs and they use to be able to administer them. Databases, normally SQLite, and things like proprietary applications as well. So this is kind of a trip back to the 90s, and this is when we first discovered some of the proprietary applications we use within IoT devices, even with current like 2018 software and hardware. Basically, it used to be like a cat and mouse game. They had these sharewares and crackers and things like this. And one of the old applications that they used to use was something called Medusa. I think you want to...
Yeah, I'll just can go through this slide. And what makes this very reminiscent of the 90s is that the people who are protecting these devices and trying to keep people out are sometimes resorting to very extreme measures. So in the 90s, we saw things like protectors of copy protections hijacking interrupts, for example, using device drivers, having to have admin privilege to even run. They were using unauthorized rights to the hard disk to sectors that weren't removed or blanked out during formatting, so they could actually keep trial time expiration dates enforced even if you formatted your whole hard drive. This was before virtual machines. So it was basically a wild west of copy protection and deprotection. On the other side, you had people cracking these protections using soft-ice and IDA, which is IDA is very potent, of course. Soft-ice was an old kernel debugger, which was extremely powerful for its time. So we see a lot of this spilling over in today's IoT world as well, with things like default credentials. But as Vlad mentioned, the Medusa protection is actually a kernel patch that we found in an IoT device. It modifies the kernel. It has its own C library, which is very stripped down and has limited functionality. It prohibits the root from even using syscalls. It runs everything in a shielded process. So essentially, it's manipulated OS functionality, which is supposed to lock down the system very, very strongly.
So every binary that runs this basically has this like Medusa header on top of it, and then it has to, the kernel agrees the Medusa header and makes sure everything is great and executes correctly. Within this particular IoT device, they had this header within every binary, but there was no CRC check for the binary itself. So you could actually just copy and paste this header on top of like any other binary you wanted, or just...
Slight modification. There is... the binaries were not CRCing themselves on runtime, and neither was the kernel patch. So when they were loaded into memory, it didn't care about the actual content of the code section or relocks. So you could actually patch out all the relocks and just write your own code into it and patch in any call to any C library you want on that. So it was, yeah. We had a few examples where we patched a few binaries beyond recognition to make it do other stuff.
So another thing that's kind of reminiscent of the 90s is like really amazing backdoors that are built in by developers. And this was actually a modded version of login binary, especially for the Linux system. Basically, over Telnet, it had a particular password it would look for. In this case, it was dbl admin. And that password actually would then run a statically generated keygen. The keygen was based on like a challenge response. The challenge was completely isolated, not based on any kind of previous user configuration. So once you stepped through the binary and understood the actual steps it took to be able to then recreate it, you could create your own key generator by simply patching the login binary and getting to output the correct key with the input. And this gave you full root access, basically, on the box.
And eventually, we actually lifted all the generation algorithms into a new binary and built a keygen for all versions that now runs in an emulation.
When we first did this, we were actually really interested to find, like, well, could we find a bunch of these devices on the internet and could we fingerprint them? Because now all these devices have root access over Telnet remotely, and the users don't actually, well, the administrators of these devices don't know that this is the case. So we looked at basically, well, trying to find different versions of this device. Of course, depending on like build options, like applications, custom adjustments, you could always be able to track down kind of what was going on. But it was, of course, quite possible to fingerprint these systems. So we built out a kind of an IoT map to try to understand where some of these systems were. And this is actually for a later talk, but this gave us an idea on IP addresses of where these things existed. So the issue is with IoT devices, no matter kind of what you do, you're always going to be running like IoT web servers. As Kelly mentioned in the previous talk, it's possible to kind of hide this and put it away, but a very easy thing to do is look for things like the BOA, the go-ahead web server, like TTPD, and that gives you a very good indication like this is an IoT device, this is an embedded device that's running a particular version or system. Another thing we found that was really useful to fingerprint was things like content lengths. So particular devices had very specific content length headers. Simply by looking at those, regardless if it was behind authentication or not, you could also very accurately identify what the device actually was, especially if you combined it with the web server fingerprints. Of course, FTP and telnet banner grabbing is quite common. It's an easy way to track down these systems. SSL certificates, very few of them had it, but if they did, you could also be able to understand exactly which device was running in each situation. And what we noticed was certain vendors actually took precautions against this. And one of the vendors was a company called GoIP, and they make a lot of these critical infrastructure devices. So they did a lot of good things. They basically they had no obvious IT web server strings, had unique content lengths, like no unique content length strings, had no initial web pages, so there was no ability to do kind of any fingerprinting, that anything came back. No kind of unique ports running by default, and no telnet banners in the newer firmware versions that were unique. So these were the good things that this company did. And the bad things that this company did is that they combined all those things together. So because they went through all this effort to be able to kind of remove any information around their systems, they actually had a very low fingerprintable system that stood out very, very clearly when even just looking over Shodan scans. So simply by looking for the words, please log in and 401, you could actually differentiate. So even though you get a lot of stuff like this, which wasn't the device you're looking for, you could very clearly see, okay, no server name, no content length, no e-tags, great. And this is 100% identifiable as that particular device. So if you do take precautions to remove things, make sure you're inside the bell curve. You're not kind of being the person that's like, I'm never going to be fingerprinted. Well, then the lack of your information is going to be what's going to be able, for us, be able to fingerprint you. Of course, there are custom protocols as well, and all of IoT devices run very unique and custom protocols, normally over UDP, which always staggers me. I understand that UDP is easier to work with. You don't need sessions. You don't need to be able to do any handshakes, but it also gives you a lot of disadvantages. UDP is very fast and very positive to scan over the internet. You can do huge net blocks with multi-threaded scripts very, very quickly. You can spoof UDP addresses extremely easily, so even if you do IP whitelisting, you can still be able to send information towards these systems and execute particular code or applications. And custom API also means custom parsers and custom implementations and custom authorization techniques, which also leave you open to making mistakes within that kind of area. So another case study was another company called Voiceblue. They make smart home systems, they make smart home routers, they make very expensive, like 600-700 euro systems that can control your home, that basically you type stuff in. And of course you also make these gateways that basically transmit GSM and SIP traffic. And this is the thing that we were interested in, were the gateways specifically. The company provided a very handy tool in Java that basically allowed you to download the tool to your home network, and then you would run it with no options available, and it would then scan your home local network, and it would tell you, oh, these are the IP addresses of where your particular Voiceblue device is sitting. By simply reverse engineering the binary and just looking at what it was sending out, you could simply change the home network to the internet, and you could create a scanner to use their own protocol to then find devices live online by simply scanning them out. So very much thanks to them, but it made things very easy. The information that came back was extremely verbose. So in this situation, all you need to do was send this particular request to a secret port that you could find within the tool, and back over UDP, you would get the description, you would get the bootware version, the MAC address, the serial number, the license active date. So in this case, this is the GSM gateway we're looking for. It's called the Voiceblue Next gateway. This is the G729, is the voice codec it uses. It uses SIP, tunneling, SMS, SMSE, and license limitation. In this case, is disabled, license status is unlocked, networks can operate in any network. So we're really thrilled. We're like, hey, let's keep scanning the internet and see what other, where we can find them. The funny thing is, because this organization makes a lot of different systems, they build things of this very particular process when they come to making these devices. So they use these systems and then they process the same way, no matter if it's a GSM voice box, it's a GSM gateway, or one of these very expensive home control systems. So the same message and works across the whole, for example, well, the whole product base. So this is the, for example, here is the 2N indoor touch, which like hooks up to your home, exactly the same message, responds in this case with a description of what it is. And then the 2N Stargate is another device that they make as well. Again, exactly the same UDP message. It responds back with information, what it does, and like the IP addresses, serial numbers, things like this. And of course, like using this information, you can then do a lot of interesting things, like calling people up and be like, hey, listen, I need a firmware update, my system is at work, and this is a serial number. Can you like reset the password, please? So yeah, that was quite interesting. Once we have these devices, like once we have ability to locate these devices, we kind of now want to get the firmware from them. And this was the next step for us, is to be able to download and dump firmware either from the firmware update process, from the manufacturer's website themselves, sometimes from live systems if possible, because we really don't want to go through and buy like 600 euro boxes and then like break them and then try to find like buy new ones. But then we wanted to basically determine dependencies, understand the architecture, and then virtualize and execute the whole device in its own like virtual environment, regardless of the processor it's running, so we could do full instrumentation and vulnerability analysis very, very quickly. So again, I won't cover this in too much detail, but we found many ways to extract firmware, command injection and IT via ping, like trace routes, logs, priv escalation via kind of these MML commands, hidden accounts and CLI interfaces. The firmware update process is a great way to dump firmware from devices themselves if you have it. Telnet FTP, priv escalation and firmware dumps. And sometimes, if you don't have access to the firmware, it's very possible to get it from a demo site. So there's another company called OpenVox, and if you go to their website, you can actually click on demo, and it will take you to like a demo device that's kind of locked down. And you can see how it works, and it's on their servers, and you can like play around with it. But they disable most of the interesting functionality for this particular device, so they actually turn it off. So for example, this is the demo site. I can show you the IP address because they've since removed the demo, and I'll show you why in a second. But as you can see, they disable the backup functionality, the upload configuration functionality, etc. But you can still do other things with it and evaluate the device to see how it works. Well, one of the things you could do with it was you could ping other systems. And in this case, you could actually just insert OS injection commands into the box. So in this case, we didn't want to buy the box, but wanted the firmware. So we could use the demo site to just have a little look around and be like, oh, great. So we can extract all the firmware via the web interface. And then from there, carry on and virtualize anything we want. But to virtualize it, of course, we need to create this virtual environment. I'll cover that in a second. Another company, again, similar to these guys, they just list all the firmware available, every single version. If you just browse to the right place, you can just download whatever firmware version you want, going back to 2015 all the way up to like the latest one. So that also allowed us to do a lot of things like diffs between different firmware and see what we wanted to run. In some cases, we did have the device, and we couldn't actually get the firmware off it. Well, in that situation, by downloading a firmware update and simply examining the binary, we could get other information to be able to then root the system itself. So IoT devices tend to have extremely a lot of hard-coded credentials. In this case, it was actually hard-coded in the binary. And we didn't really need to understand the MIPS architecture to be able to look at this and be like, hey, I think this is probably something we can use to dump the firmware from this device. So we have please input password. We have a string compare happening here, star wdin star hashtag, another string compare, and password is invalid. And if the password is valid, it drops you into SSH and root, and then you're like, hey, fantastic, I can now dump the firmware again. So you don't actually need to buy a system to be able to then do IoT research, which is great for us because we're kind of cheapskates. And this is kind of, I think, the takeaway from this idea is that the nature of an IT device is like it's a system that will run in a hostile environment with no controls or oversights, with people who are operating it who have no idea what they're doing. And I think it's important to kind of embrace this reality and not spend time on stopping people from getting access to your systems or your firmware being rooted, because it will happen. It will happen very easily and very quickly. And the idea is here, build secure binaries without hard-coded credentials, without like things inside that you can actually give to people and say, hey, you can have my binary, but it doesn't make my system any less secure, because I'm not running any secret UDP protocols, I'm not running any secret IP systems or users or anything like this. And that's where I think the time should be spent, not the time in obfuscating things. So now we have firmware, some from live systems, some from not live systems, some from updates, and now the next step is basically determine dependencies, understand architecture, virtualize, and execute these particular systems. The question then arises, why virtualize firmware? Well, as I mentioned before, sometimes we don't have access to the actual hardware. We don't want to break expensive devices. I've done that many times by like sending like fuzzing traffic towards a system that I got, and it just breaks, and I have nothing else left but a heavy paperweight. Take out the binaries, and we can run them on our own systems and do much better instrumentation. We can do debugging, we can do fuzzing, we can research purely based on firmware updates, and we can find generic vulnerabilities for multiple sets of systems by looking at the base firmware that all these devices are built upon. And that gives us a really good coverage across many, many vendors. So I think I will hand over to Fred here and talk about a little bit how to understand like what's under the hood and actually go through the virtualization setup of a full testbed environment.
Sure. So what does it take to virtualize an environment for this, or at least virtualize part of the firmware? So you can run certain components, like if you have a web server, you might want to run that. If you have a database program, you might want to run that. Well, knowing the processor and architecture, so you can actually attack it and understand what it does, you need to have a Linux distribution that somewhat matches the one running on the device. So if it's running on gclib, then you should have that, glibc, or if it's using uclibc, you should have something running that. And then you have to get your firmware components onto this emulated device, and quite often, that's actually enough to make something run so that you can break it. IoT hardware is a little bit different than regular x86 stuff, so the general purpose hardware that we use every day. So you need to learn a little bit about a new instruction set. But first of all, you need to know how much you need to know, which is probably less than you think. And you need an environment to make your prototyping in. So if you find a vulnerability, you need to make sure it runs and try it out and customize it so that it runs properly. So you need something like a malware factory, which is what we built. So the malware factory is a set of 14 different processors, or flavors of processors. So we have ARM, ARM thumb, 64-bit ARM, MIPS. We also have 68K, PowerPC, and Spark. Spark is more geared towards telco infrastructure, of course. That might still be running Solaris and things like this. But for IoT devices, we have these processors. It's not just a tool for testing and developing. It's also a tool that helps us learn how to learn. So we also included some of these conceptual processors like Extensa or Microplace. So even if you never actually run code on such a machine, it's good to get to know how that machine sets up a stack, how it returns from a call, how it passes parameters to itself, and et cetera, because most processors are very, very similar in this respect. So like I said, we have 14 supported processors using QEMU. Each of these processors has a limited tool chain attached to it, so we can actually cross-compile or cross-assemble for each of these chips, so we can instantly build a new test snippet. Each of these processors come with a dedicated loader that actually loads this test snippet. So we assemble a code, strip all the ELF stuff out, and only leave the code section. So we can have a delta offset coded relocatable piece of code that runs when loaded into memory. So the loader actually just loads a binary chunk into memory, calls it, and doesn't care what it is, and then returns, hopefully, if we write our snippet correctly. It also has file sharing between host and guest OS, so that it can exchange files easily. So you can actually build on the host using the cross-compile tool chain, and then you run it immediately on the guest. So it makes it less of a chore to actually develop things and try things out. So the loader is not so complicated. It's essentially just opens a file specified by the first argument. Then it loads it into memory. It then adjusts the protection of the memory chunk that it's loaded so that it's executable, because in some of these devices, very rarely, you have memory protection, usually not. And then it calls the, it calls the buffered data with print as the only parameter, so that you can actually do some debug output or print success, hopefully. Another nice feature is that you can actually do live debugging using the GDB supported by Qimo. So just add this to your Qimo command line, and you can do live debugging of your payloads, which is also very nice. So we have a short demo of the malware factory as well. So I'll leave my OS X qualified assistant to start. See if this works. Let's hope it does. Okay, so this is whenever we are in the launcher or the guest OS, the text will be white. Whenever we're in the host or assembling some code, it will be orange. So we have some kind of differentiation. And when I made this demo, I didn't really think about it, so I put the sort of indication text in orange all the time. But it's the text of the interface that matters. So here we'll start first the x86 emulation, which should be familiar to most people, I think. So start out this mini Linux distribution, which is built in BuildRoute. The home ASM folder is shared between host and guest, so you can just go into that and adjust or rebuild things. So here we'll just use the loader first to load the payload for the x86 code. And that's basically how you execute it. And now we'll go through the source of the x86 binary. So it's very, very basic. It sets up a stack frame. And all of these examples, we have an example for all of the chips. And they do essentially the same thing. They set up a stack frame, as it's more or less supposed to be set up. It then pushes the parameter, or passes the parameter to the call, because not all are pushed. Only, in fact, x86 is pushed. In this case, we use call and then call over the actual data that we want to pass to the call, because that's a function of the Intel instruction set. We then call the first parameter on the stack, which is pointed to by the base pointer, +8, which is print that the loader passed to the snippet. And then we restore the stack frame by leaving and returning gracefully. So that's for x86. We can then compare that to how it would look on, well, now first I will show you how it rebuilds. So it's very easy to modify. You just run make, and it compiles the binary, strips the of stuff, and then you can call it again. So it's instant almost. As for x64, it has a very similar look and feel to it. And instead of using EBP, it uses RBP, of course, so it's the 64-bit versions of the register. The text parameter for print is pushed in the same way, but since 64-bit Linux uses fast call, we instead have print in RDI. So we pop the pointer to the string text into RDX, and then we exchanged RDX for RDI to make sure that the first parameter for print is pointed to by RDI. And then we call RDX, which is print, and then return exactly the same. So this is the basic example that comes with every chip. So for ARM, it will look a little bit different. It starts the same, of course. Has the same features, has the same sharing between the guest and host. So we'll just go into the appropriate folder. And we'll just cross-assemble it, of course. And again, the binary is built instantly. And you can run it, and it does the same thing. And then we have a look at the source code, which looks a little bit different. So here the stack frame is, you start by saving, for example, the stack pointer in R12. Then we use this registry saving function. And then we allocate some stack space using subtraction of the stack pointer. We move the first parameter into R2, which is the print, of course. Then we take the content of R3, which is the register that the loader uses when it calls this function. And then we call R2 with the pointer to this text. The pointer to the text is derived a little bit different in this case. we don't have the luxury of using the return register to get the parameter, so instead we jump over it. And since we have the address of the main in R3, we just add 4 to it, because ARM is a 4-byte fixed size instruction set in the normal case. In thumb is, of course, variable size. So, yeah, once it has called print with the pointer to the text, it then restores the stack by adding to the stack pointer and then restoring all the registers, including the program counter. So this is it shows a little bit how the stack is set up and also where you would be finding the return address, etc. Again, it's very easy to just rebuild it and modify it and make it do other things. And there is a loader for each of the processors as well, and there's an examples code snippet for everyone. We can have a look at...
I think let's do this and then move on after this one.
Yeah.
Time-wise.
Exactly. So this is the variable size instruction set for ARM as well. It looks a little bit different, but it does the exact same thing.
Basically what it means now, you can cross-compile for any process you want. You can launch whatever emulation environment you want.
Yeah.
And you can build, you can run binaries, you can virtualize like whatever IT device you have, regardless of what processor it's running on. Makes it very easy to then actually set up and run these systems.
Yeah. And being familiar with the BuildRoute toolchain as well makes it possible for you to actually build for C as well. So you can build more complex things if you want to install your own little rootkit on an IoT device, etc. You can build for it.
So the reason we called this initially Malware Factory was because we were building a particular rootkit for a number of IoT devices, and they were using different processes, different architectures. We wanted to go through and understand how that would work across these different systems.
Yeah. When setting up this kind of VM, we wanted to keep it small, so the whole thing, including all the 14 different emulations, is 280 megabytes. So it's very light, but then we had to strip out all the GUI stuff and everything like that. So we had some trouble getting the right terminal outputs and things like that. So it took a bit of tuning, but it's very comfortable now that it works.
Like wanted to set up now, for example, go and download a piece of firmware or a firmware update, and we can actually run a particular, like the firmware binary for the web server, for the API, for something else. Just throw it in there. It normally executes, it points to the right libraries, and it's kind of good to go. So it makes it a really nice and easy process to go through that. So yeah, as I mentioned, it allows us to build code snippets. We can debug code snippets very quickly. Sometimes it allows us basically to run like the full component from the device as well. So we've used this to do fuzzing across like the web servers the devices are running, and the way they actually built within the device as opposed to downloading the source code of the web server. Because a lot of the time the manufacturers will actually adapt the code, they will change it, they will add things, they will add particular bits and pieces and take things away. So it makes it much more reliable to be able to do this kind of instrumentation.
So yeah. So what do you need to know to be able to program assembly for a new chip? Well, it's actually a lot less than most people think. We notice that people are a bit afraid to jump into a new architecture, but what you really need to know is how to load and store between register and memory, how to load an effective address into memory, or an immediate, of course, how to shift bits left and right, and shifting is important when loading, let's say, a 32-bit integer into a 32-bit register in a fixed size instruction set. Because you have a 4-byte instruction, and you have a 4-byte size integer. So that leaves no byte for the opcode. So you have to load half the integer first, shift it left or right, whichever you, roll it right then, I guess. But shift it left, and then add the second part. So you build it incrementally. Performing and or add and subtract, of course, very important, especially and. And then you need to be able to branch both by displacement and by content of memory location when you're talking about imported functions. And by register, of course, as well. And you need to know how parameters are passed to a call or a syscall, if they are passed through the stack, if they are passed through registers, and which registers they are passed through. And you need to know a little bit about the stack frame and the relevant registers. So that would be the stack pointer, of course, the base pointer, and then hopefully a little bit about which parameter registers are used for fast calls, and non-volatile registers. Which registers do I need to preserve to not break stuff? So loading data from a register to memory would be the equivalent of the 16-bit x86 instruction moving from location 1000 to AX. Storing would be exactly the inverse, storing AX into address 1000. And locating these type of instructions in ARM or MIPS is quite easy once you know that you need them. Shifting would be, well, loading effective address, the LIA instruction. This could be either using an equivalent instruction or loading an immediate address into memory if you know what you're looking for. So shifting bits, of course, it's the equivalent of shift left and right, and there is sometimes a bit of problems with arithmetic and normal shift. So you have to determine which one is being used. This is something that I ran into on the Go IP, actually. Performing AND and OR instructions, it's the same thing there, being able to AND or OR, just like in x86. When it comes to branching, you need to know what's the branching.
So basically, you need to know which branches to jump, with conditional, unconditional, and what the equivalent jump call would be as well.
Yeah, exactly.
And basically, yeah.
And
finally,
then branch by register.
Yeah, you need to also know how to branch by the register as well. Regarding this, I think we'll probably cover this quite quickly.
Sure, we can do that. How parameters are passed. This is an example from x64. It's using registers. Most ARM implementations do that as well. Same thing for MIPS, using the lower registers and then up. So this is, yeah. Once you see one of the procedure calls, you can actually determine this quite easily. And the stack frame, we looked a little bit at that. If there would be time, we could look more at each of these examples, but let's just leave that. We went through this a bit in the demo.
So yeah, it's basically, set size will be up, but this is different calls and stack frames for basically each processor. And if you're interested, yeah, please feel free to have a look at them. And it gives you the ability to be able to start coding and assembly for these different processors very quickly and understand what's going on within them. So for ARM, for MIPS, and for the 14 other ones that are in there.
Yeah.
So what do you actually need to know? Well, you actually don't need to know that much to be able to do this. You just need to know like a few of the pieces, need to know how to read this assembly, produce very basic assembly, understand like the procedure and entry return procedures, how things branch in, branch out, and patch and modify that binary. So that's the easy and the fun part once like all the other stuff gets understood. Probably do this on your machine. We could do this at the end, but basically we've virtualized one of the devices we found online and just running it inside the emulate it completely, so then we can do full testing of this particular device. So what next? Well, after you virtualize it, what can you do? You can lift algorithms, you can lift procedures and functions. Once you start lifting relevant functions, you basically fuzz them offline. You can go through and single step each function to understand what's happening, and the VM can really basically speed up this process. What we mean by this, basically having direct access to the development tools, you can step through and host multiple applications for these lifted functions. So you can run and set up 20 of these virtual machines. They're very small, they're very quick to run. You can run them in parallel, and you can go through and fuzz each one of them for different parts of the application. If one crashes, you can go and examine that while keep the others going. So it gives you a lot of flexibility to quickly understand issues within the IoT devices themselves. And of course, I mentioned before, there's no risk of actually taking out your device, which I've come across multiple times. No downtime. You have the ability to snapshot to restore corrupted VMs very quickly. And of course, kernel debugging within QEMU and with full like GDB support. And the result of this, we basically came across and we found multiple DOS vulnerabilities using like single UDP packets towards many of these devices that run custom APIs. You can simply send a crafted packet and take it completely offline, including full-on servers that use x86 as a processor and like have a lot of memory and setup behind them. You can DOS, we have new vulnerabilities like go-ahead web server, again single DOS packets there, and I think for light TTTB server as well with a particular setup in an application. Basically, the ideas behind this, well, it's not too difficult to virtualize and execute custom IoT components. Means fuzzing and attacking IoT systems becomes much easier. And it's kind of looking for bugs outside with just the default password and the basic things that hopefully will get fixed very quickly. And hopefully people will start fixing those. And as mentioned before, the idea is basically focused on making the binaries resilient as opposed to actually obfuscating and creating resources within them. The other reason I want to mention is we built this system is also because within the telecom world, you really cannot afford to buy things like MMEs or HSSs or HLRs to test and and attack. The vendors don't like to give you to them, and the people who work with and the telecom operators, they don't like to give you the access to test on their test beds because these are like very, very expensive elements that cost hundreds of thousands of dollars. But during testing, you can lift firmware of these elements, and you can take firmware back, and you can set up your own instrumentation. So you actually then use similar methodology that we use to test things like network devices within core networks that you would otherwise never get access to. Awesome. Thank you so much for your time. And are there any questions?
The malware factory, is it your own tool or you're releasing it as open source?
I think eventually we'll be releasing.
So the malware factory, again, will it be open source or you're using it as your own tool? So what's your plan about this?
Well, we haven't discussed that in depth, really. It's a tool that we use for learning and for exploring. So it's, yeah, that's up in the air still, I think.
I think eventually we'll be releasing it as open source to be able to set up an instrument, yeah, for people to do that.
It's a big opportunity for other people to commit and then
Exactly.
add
other processes or architectures, yeah.
Sure.
So I think the plan is we'll be like to release that and like let people actually use it and play with it.
Any more questions? Well, then, thanks, Vlad. Yeah, sorry.
There's a lot of different devices out there. Do you think there are some categories that are better to look at? If I wanted to start looking at something.
Categories of devices?
Like we have network equipment, we have CPEs, we have professional equipment.
Oh, I would go for anything that you can download firmware from. You can try it at home.
Just anything.
Yeah,
I thought this is anything that's connected like to management networks. I think it has to be connected to the internet makes things a lot more interesting because you feel like you have an impact there, and you can also understand the impact in a bigger way. So like for me, it's personally interesting to look at devices, how they're spread out, where they are, and ones that are like normally accessible remotely. But yeah, if you're interested in that, definitely like look at some of the fingerprinting methods, pick a couple of like IoT web servers, and you'll be able to see different like IoT implementations. And you'll even using Shodan, you'll quickly see just patterns of devices, and you'll be like, okay, this is this type of system, this is this type of system, and even just like looking at HTTP ports across different countries, you'll again identify them very, very quickly. So yeah, I'd say look for those and look for ones you can get firmware updates from the manufacturer. Of course.
Yeah, then thank you both. Then we are done for today. Hope you enjoyed the day. Please, if you can, join us for the German night, which starts at 6 p.m. Downstairs. Have a great evening, and tomorrow we will start at 9 a.m.
Awesome, thank you very much.
Thank you very much.